Hello everyone, my name is Nadir. I am a PhD student in the University of Brest in France, and I am glad to participate in this interesting conference. The topic of my PhD thesis is about energy management in small electric UAVs, called also drones. Today, I'm going to give a presentation about a frequency separation rule-based energy management strategy for a hybrid fuel cell powered drone. For the presentation, I have adopted the following plan. I will start with a short introduction, followed by a state-of-the-art on the electric drones, where I will talk about their different applications, architecture, and energy management strategies. Then I will present the study we have done in our paper. And I will finish by conclusions and perspectives. Drones are considered as flying robots that can perform multiple missions when equipped with different sensors and actuators. In 2020, the drone market is estimated to reach $127 billion. As shown in the figure, different international companies are investing in different areas, such as delivery, mapping, and inspection, as we can see in the figure. For the state of the art, we start by citing the different applications for drones. For the civil sector, we find agriculture, delivery, telecommunications, where drones are used as the relays. We find also inspections, either traffic or electrical systems, such as wind farms or PV farms. We find also videography or photography, where the drone is used for production of films and documentaries and so on. Meteorology, when the drone is used in the study of atmospheric phenomena and also for weather forecasting. Pollution level detection also is an application for drones in civil sector. For the military field, we can cite medical supply on the battlefield, communication disruptors, small spy drones, maritime applications. We find also raking, border surveillance, reconnaissance, and data transfer relay. Drones can also be used to collect data for scientific purposes. They can operate in places where direct human intervention is either impossible or very dangerous, as we can see in the figure. Different classifications can be found in the literature for drones by considering different criteria such as size, endurance, and architecture. As illustrated in the figure, we can see drones with wings or with multi-rotors. We can find heavy or light drones. We can find high or medium altitude drones, and so on. It depends on the criteria. We can define each classification. A typical drone has an architecture that includes the following elements: the flight control system, communication system, which allow communication with the ground control station. We find also data storage system, and also we find the propulsion system, which is the most important part for our study. The propulsion system includes power sources, power converters, include also propulsion motors, and the energy management system and speed controllers. The drone's propulsion can be provided by internal combustion engine, which has the advantage of high energy and power densities, allowing a large autonomy. However, combustion engines have some disadvantages, namely low efficiency, thermal and acoustic signature, which makes them easily detectable, which is not good for military applications, and also a negative effect on the environment. The electric motor overcomes these limitations and offers essential advantages for drone operation, despite the fact that it does not have enough energy density compared to the combustion engine. The brushless DC motor is mostly used for electric drones. It is characterized by a high efficiency, low maintenance cost, ease of control, and high power density at reasonable speeds. Some drones have the possibility of being recharged in flight by laser systems and then increasing their endurance, but at the same time reducing the flight range and introducing more constraints on operation. Energy management strategies are mainly divided into two classes, active and passive. In the passive case, power sources are directly connected to the DC bus, while in the active case, power converters link the power sources to the DC bus. As we can see in the figures, here we have power converters, and here we don't have power converters. Sources are directly linked to the DC bus. In the passive case, the sources operates according to its own characteristics, while in the active case, an energy management system efficiently manages the power flow. The passive system requires a strict dimensioning of the sources, and it is not that safe in terms of security. The active system is heavier and more complex due to converters. Power conversion losses will be eliminated in the passive case, when in the active case, the lifetime of the sources will be improved and the energy will be optimally used. For our study, a proton exchange membrane fuel cell is combined with a battery and supercapacitor. The fuel cell delivers power through a DC-DC boost converter, allowing to control its output current. The battery operates as an energy buffer with its bidirectional converter, which enable the regulation of the DC bus voltage. Consequently, the battery can be undersized. The supercapacitor, it is used as a complementary power source, delivering or absorbing high frequency components with rapid response relatively to the battery. A dynamic load was implemented to simulate the drone power demand. A real load profile is used for the simulation, which is the result of an experimental test of the drone shown in the figure. The flight test took place in Salento University in Italy. The power profile obtained is presented in the figure, and its characteristics are listed in this table. It is worth mentioning that it is possible to extract another load profile for larger multicopters by considering the proportionality between the power required and the weight of the drone by a factor of 2/3. For the energy management strategy, the frequency separation method was firstly adopted. The power demand will be separated in high and low frequencies using a low-pass filter. As the fuel cell, it is considered as an energy source characterized by a relatively long response time. So it will deliver the low frequency components. The storage system composed by battery and supercapacitor play the role of power source with a reduced response time. It will deliver or absorb power peaks. This leads to a smooth power profile for the fuel cell, as we can see in the figure. The power profile for the fuel cell, it is less harmonious than the power, the demand power. We combine the rule-based strategy with frequency separation. The load power will be first filtered before being considered as a decision variable with the state of the charge of the battery. So we have two decision variables, the filtered power profile and the state of the charge of the battery. According to this, to the possible values of these two variables, we have defined 6 decision sectors to calculate the fuel cell power references. As we can see in this figure, the defined rules allow to the fuel cell operating in desirable operating points where the efficiency is high. A minimum and a maximum power limits must be respected. We have P fuel cell max and P fuel cell mean and P fuel cell optimum, which is the nominal power for the fuel cell. Beyond these limits, fuel cell output power will be limited or will be saturated. In addition, a minimum state of charge is maintained throughout the entire mission for safety reasons. We take this value of 60% for our study, and the maximum state of charge, it was taken 90%. For the simulation, we have used the models available under Simulink for the power sources, and for the converters, we implemented average value models which enable to accelerate the simulation time compared to switching models, while maintaining the conversion dynamic. Switching models are generally preferred to design studies, which is not our case. Three scenarios were considered in the simulation depending on the initial state of the charge of battery. 40% means that it's below the minimum value, 70% in the normal range, and 95% means above the maximum value. It is observed in the power response that the fuel cell power follows well the energy management strategy rules. It supplies according to the predefined operating points, nominal power and minimal power. Outside these points, the fuel cell can either supply the needed extra power to charge the battery when its state of the charge is low, or follow the load power when the state of the charge is high. The difference between the load power and the fuel cell power is supplied or absorbed by the energy storage system. The supercapacitor operates as a complementary power source, delivering high frequency components. The low frequency components were handled by the battery and the supercapacitor with the slow response. The response of the supercapacitor is slow relatively to the supercapacitor. Because of that, we can observe that the battery power response curve is less harmonious than the supercapacitor's one. It can be noticed that the fuel cell operates well as the primary energy source, when the supercapacitor operates as a secondary high frequency power source. The DC bus voltage, which is the same as the supercapacitor's one, is regulated around the reference value of 55 volt. And the DC bus regulation could be more strict, but it is preferred to allow to the supercapacitor a small interval of voltage variation to enable it contributing in the power supplying, especially delivering or absorbing power peaks. It can be concluded that the power delivered by the fuel cell complies well with the rules defined by the energy management strategy and operates within the permitted range. The battery allows the regulation of the DC bus voltage around the reference value and also the smoothing of the power profile of the battery. Similarly, supercapacitor as a complementary source handles power fluctuations by smoothing the battery and fuel cell profiles. This reduces charge and discharge cycles, and then it can increase the battery lifetime. For the perspective, we will work on the implementation of an energy management strategy and the purpose will be to improve the UAV or the drone autonomy. We will work also in development of an emulator for specific type of drone dedicated to inspection missions. Thank you very much for your time and your attention. It was a pleasure to me, and see you next time.